In a plant, vital process variables such as pressure, temperature, level, and flow are monitored and controlled by process instrumentation. By providing valuable information about process variables, instruments help operators to maintain safe and efficient control over plant processes. It's important for operators to have a good understanding of how process instrumentation works. Accurate level measurement makes it possible to ensure that proper amounts of materials are maintained in process systems. It also provides a way to determine the amounts of raw materials available for processing and the amounts of finished products or waste materials that are produced. Simply put, the level of a liquid or a solid is the position of the surface of that substance above or below a fixed reference point, often called the 0 point. For example, if the 0 point for this container of liquid is at the bottom of the container, then the level measurement is taken from the 0 point up to the liquid surface. On the other hand, if the 0 point is at the top of the container, then the level measurement is taken from the 0 point down to the surface of the liquid. For some processes, you may need to monitor the level of a material continuously. Other times, you may only need to know when the level reaches a certain point. For that reason, level measuring instruments may be designed for continuous level measurement or single point level detection. Here's an example of continuous level measurement. In this arrangement, a gauge that's mounted at the 0 line of a tank provides an indication of the level in the tank at all times. If the level rises, a pointer on the gauge moves up a scale to indicate the higher level. If the level drops, the pointer moves down the scale. Here's an example of single-point level detection. In this arrangement, an electrical probe is used to detect a single predetermined level in the container, in this case, a high level. If the level of the liquid in the container reaches the predetermined point, the level measuring instrument activates a high-level alarm. Some level measurement devices measure the actual level of a substance directly. These types of devices are called direct level measurement devices, and there are many types of them used in industry. One example of a direct level measurement device is a plumb bob. A plumb bob has a weight that's attached to the end of a reel of flexible measuring tape. To measure the level of liquid in a container, the weight is lowered into the container until it touches the bottom. The tape is then reeled back in, and the level is read directly at the wet line on the tape. This gauge glass, or sight glass, is another example of a direct level measurement device. It's a transparent vertical tube that's attached to the side of a tank. It's connected to the tank with pipes at the top and the bottom of the tube. The use of a gauge glass is based on the principle that liquid levels equalize in containers that are connected together. In other words, the liquid is free to move between the tank and the glass. So the level that's visible in the glass is the same as the level in the tank. Here's another type of direct level measurement device. It's called a float and cable or float and tape device. This housing contains a reel of tape and a mechanical indicator. The tape runs from the take-up reel and indicator through a pipe into the tank. Inside the tank, the tape is attached to a float. When the level of the liquid rises, the float rises with the liquid. The take-up reel reels in the slack tape, and the mechanical indicator displays the new liquid level. Electrical probes, such as these conductivity probes, are another type of direct level measurement device. They're used with liquids that can conduct electricity in order to complete an electrical circuit. As this illustration shows, the conductivity probes are connected to a high and low level alarm. A current flow return path from the tank is also connected to the alarm. The two probes are mounted on top of a tank, and they extend to the minimum and maximum points to be measured in the tank. As long as the liquid level is between the upper and lower probes, current flows from the low-level probe through the liquid and back to the alarm. This is a normal condition, so no alarm is activated. But if the level falls below the lower probe, the circuit is interrupted, the current flow stops, and the low-level alarm is activated. The alarm will remain activated until the liquid level returns to normal. Now, if the liquid level rises and contacts the upper probe, a different circuit is completed. As a result, current flows from that probe through the liquid and back to the high-level alarm, activating it. Indirect level measurement devices do not measure level directly. Instead, they measure a physical aspect of a liquid that varies in proportion to level. Then they use that information to provide a level measurement. The physical aspect that's usually measured by an indirect level measurement device is pressure. This illustration shows an example of an indirect liquid level measurement device. It's a gauge mounted at the zero line of a tank. The gauge uses the hydrostatic pressure of the liquid in the tank to indicate the liquid's level. The amount of hydrostatic pressure that's exerted by the liquid depends on the liquid's height. So, as the level of the liquid varies, the hydrostatic pressure varies as well. The gauge converts the hydrostatic pressure to a continuous level measurement indication. An indirect liquid level measurement device called a bubbler system uses hydrostatic pressure in a slightly different way. It operates by forcing air out of a pipe that's immersed in liquid. The system consists of a pipe that's open at the bottom and connected at the top to a regulated air supply. There's also a pressure-sensitive gauge, which is used to indicate level. The opening at the bottom of the pipe is at the minimum level to be measured in the tank. The level of the liquid in the tank can be measured by adjusting the air supply until bubbles slowly come out of the bottom of the pipe. At that point, the air pressure felt by the gauge represents the amount needed to clear the pipe of liquid. The gauge uses the pressure that's exerted on it to provide an indication of the level of liquid above the opening in the pipe. Pressure gauges and bubbler systems are used in applications where the tank is not pressurized. They're not designed to measure the levels of liquids under pressure. However, if a liquid is in a pressurized tank, its level can be determined by using a differential pressure device that's sometimes called a DP cell. A DP cell, like this one, measures the difference between two related pressures. We can see how a DP cell works using this simplified illustration. Here, one side of the DP cell is connected by tubing to the upper part of a tank. The other side of the DP cell is connected to the lower part of the tank, near the bottom. The liquid in the tank exerts hydrostatic pressure on one side of the DP cell. When the tank is pressurized, additional pressure is exerted on the liquid and the DP cell. This additional pressure is also exerted through the tubing from the top of the tank to the other side of the DP cell. The DP cell measures the difference between the combined pressure at the bottom of the tank and the pressure exerted at the top of the tank. That difference is equal to the hydrostatic pressure of the liquid, which can then be converted to a level measurement. In this topic, we talked about what level measurement is, and we discussed two forms of level measurement commonly used in industrial applications: continuous level measurement and single point level detection. We also looked at the basic operation of several different direct and indirect liquid level measuring devices. Now let's try some practice questions. Here's an example of continuous level measurement. In this arrangement, a gauge that's mounted at the zero line of a tank provides an indication of the level in the tank at all times. If the level rises, a pointer on the gauge moves up a scale to indicate the higher level. If the level drops, the pointer moves down the scale. This gauge glass or sight glass is an example of a direct level measurement device. It's a transparent vertical tube that's attached to the side of a tank. It's connected to the tank with pipes at the top and the bottom of the tube. The use of a gauge glass is based on the principle that liquid levels equalize in containers that are connected together. In other words, the liquid is free to move between the tank and the glass. So the level that's visible in the glass is the same as the level in the tank. An indirect liquid level measurement device called a bubbler system uses hydrostatic pressure in a slightly different way. It operates by forcing air out of a pipe that's immersed in liquid. The system consists of a pipe that's open at the bottom and connected at the top to a regulated air supply. There's also a pressure-sensitive gauge, which is used to indicate level. Most plants have miles of piping to carry fluids to and from different pieces of equipment. In many cases, it's important to be able to measure the flow of fluids to determine how much fluid is used, moved, or produced. Fluid flow is a general term that's often used to describe the movement of a fluid, which is a liquid or a gas, from one point to another. A flow meter is a device that's capable of measuring fluid flow. Two types of flow measurements that are often made are flow rate measurements and total flow measurements. Flow rate can be thought of as the amount of fluid that's passing some point at any given time. Total flow, on the other hand, can be thought of as the total amount of fluid that has passed a designated point. Different types of meters can be used to measure flow. For example, this particular meter measures total flow. This meter measures both flow rate and total flow. It measures the flow rate in gallons per minute, and it has a counter mechanism that keeps track of the total flow in gallons. Many kinds of flow meters measure flow by physically separating the fluid into specific quantities that can be counted and passed on. This principle of operation is sometimes called positive displacement, and it involves measuring individual amounts of fluid so that a total flow value can be determined. Since these types of meters in essence measure fluid flow directly, we'll refer to them as direct flow meters. This oval gear meter is one example of a flow meter that uses positive displacement to measure total flow. As this simplified illustration shows, there are two oval gears inside of the meter. The flow of the fluid causes the gears to rotate. As they rotate, specific amounts of fluid are trapped in the chambers between the gears and the meter body. So each time the gears rotate, a precise amount of fluid is passed along. If the flow increases, the gears speed up, but they still pass the same precise amount of fluid along with each rotation. A counter mechanism counts each rotation of the gears to determine the total flow of fluid through the meter. Another example of a flow meter that measures flow directly is this nutating disc meter. It gets its name from the action of the disc, which can be seen here. The word nutate means to wobble or roll about an axis of rotation. During operation, the disc rotates much like a slowly spinning top. As the disc rotates, specific amounts of fluid are trapped above and then below the disc. An increase in flow will cause the disc to rotate faster, but the same amount of fluid will be passed along with each rotation. The nutating disc meter counts the precise amounts of fluid passing through it to determine total flow. Some flow meters do not measure the flow of a fluid directly. Instead, they measure some physical aspect of the fluid, such as velocity, pressure, or level, and then convert that measurement into a corresponding flow value. In other words, they provide a flow measurement indirectly. For that reason, we'll call these types of meters indirect flow meters. Here's one example of a device that provides a flow measurement indirectly. In this arrangement, a thin plate with a hole in its center, known as an orifice plate, is used to restrict the flow of fluid through a pipe. When fluid flows through the orifice, the pressure on the upstream side of the plate is greater than the pressure on the downstream side. The difference between the two pressures is proportional to the flow rate of the fluid through the plate. The greater the difference between the two pressures, the greater the flow rate. A differential pressure, or DP cell, measures the difference between the two pressures and converts that value to a flow rate signal. The flow rate signal can be used to provide a local indication, or it can be transmitted to a remote indicating device. Now, in this example, an orifice plate was used to create a differential pressure, but other pipeline restrictions can be used to accomplish the same thing. Another type of flow meter that uses differential pressure to measure flow rate is a rotometer. In a rotometer, fluid passes through an inlet and enters a tapered tube. Inside the tube is a plummet or float that acts as a restriction in the flow path of the fluid. Fluid flow through the tube causes a differential pressure to develop across the float. The differential pressure causes the float to rise and fall as flow rate changes. The greater the flow rate, the greater the differential pressure and the higher the float rises. If the flow rate decreases, the float drops. The tube has a scale next to it that indicates the rate of flow. Flow rate readings are generally taken at the widest part of the float. Now, not all flow measurement devices are used to measure flow in enclosed passages like pipes. Some are used in open passages. These devices are often called open channel flow devices. One type of open channel flow device uses a weir. A weir is basically a dam with a notch at its top. In this arrangement, The level of the fluid behind the weir is used to determine flow rate indirectly. A weir works like this. When fluid enters the channel, it builds up behind the weir and overflows through the notch. The level in the channel stabilizes when the amount of fluid flowing through the notch equals the amount of fluid entering the channel. If the flow rate of the fluid entering the channel increases, the level behind the weir rises until an equal amount of fluid flows through the notch. So the level of fluid behind the weir is directly related to the flow through the channel. A level measuring device continuously measures the level behind the weir and converts that value to a flow rate signal. The signal is typically transmitted to a recorder where it can be read. Another group of flow meters uses fluid velocity to determine flow rate. Now, keep in mind that flow rate and velocity are not the same thing. The flow rate of a fluid is the quantity of fluid that flows past a given point at any given time. Velocity is the speed at which fluid flows. An example of a meter that uses fluid velocity to determine flow rate is a turbine flow meter. As this simplified illustration shows, a turbine flow meter has blades that are attached to a rotor. The rotor is placed in the path of the fluid flow. As fluid passes around the blades, the turbine begins to rotate. The speed of the rotation is proportional to the speed of the fluid. The number of rotations that the turbine makes is converted to an indication of flow rate. In this topic, we talked about what fluid flow is, and we looked at some of the devices commonly used to measure fluid flow. We categorized the devices that we saw as direct flow measurement devices and indirect flow measurement devices. Now let's try some practice questions about flow measurement. Two types of flow measurements that are often made are flow rate measurements and total flow measurements. Flow rate can be thought of as the amount of fluid that's passing some point at any given time. Total flow, on the other hand, can be thought of as the total amount of fluid that has passed a designated point. The nutating disc meter counts the precise amounts of fluid passing through it to determine total flow. When fluid flows through the orifice, the pressure on the upstream side of the plate is greater than the pressure on the downstream side. The difference between the two pressures is proportional to the flow rate of the fluid through the plate. The greater the difference between the two pressures, the greater the flow rate. A differential pressure, or DP cell, measures the difference between the two pressures and converts that value to a flow rate signal. The flow rate signal can be used to provide a local indication, or it can be transmitted to a remote indicating device.